This is a question from Jun07, question 5. Real batteries have internal resistance. Such a battery has an EMF E and the potential difference across its terminals is V. There is one situation where E has exactly the same value as V. What is this situation? So that situation is whenever there's no current being drawn from the battery. And when that's happening, we say that it is an open circuit. So it's a situation, an open circuit situation. In other words, when no current is being drawn from the battery. In other situations, E and V have different values. State whether E is always greater than V, always less than V, or can be greater or less than V. Indicate your answer by placing a tick in the appropriate box. So you know that E is always greater than V because whenever there is a potential difference drop, then you also have an internal resistance in the battery, and therefore V is always less than E. So we're going to tick that box, and one wee short explanation as to why that is. So the reason is because the current has to pass through the internal resistance of the battery. And we call that small r. And therefore, and this causes a potential drop or some voltage to be lost, a potential drop or a drop in potential. 4 identical cells, each of EMF 1.5 volts and the same internal resistance are connected in series with a lamp. When the current in the circuit is 0.48 amps, the lamp is operating at a power of 2 watts. So I'm just going to draw a wee quick circuit there. I'm just going to draw one single cell and I'm going to write that it's got 6 volts in total. I'm going to draw a single resistor beside it, and that's meant to represent its internal resistance. And so each of them, we don't know what the internal resistance is, so we're going to write that there's 4R there. And I don't know what it is, I shouldn't have written an equal sign. And then I'm going to put a lamp into the circuit, and I'm going to put on the current is 0.48 amps, and the lamp has a power of 2 watts. So calculate the resistance of the lamp. So we know a current, and we know a power, so we can use P is equal to I squared R. So we'll work out R is equal to P over I squared. So irrelevant, it doesn't matter what the internal resistance of the voltage or of the EMF is here. We don't have to use it in this part of the question, so we can just work ahead. So P is equal to 2 watts over 0.48, which is squared. And that gives you an answer of 8.68 or 8.7. To 2 significant figures. Then it says, hence calculate the internal resistance of each cell. So if we just use our equation, we know that EMF is equal to I times capital R plus I times small r. And so we know that 6 is equal to, the current is 0.48 times, and we've got a resistance up here, which is 8.7. And then we're now talking about the small internal resistances, and because there's 4 of them, I'm going to put a 4 in front of it. It's 0.48 multiplied by 4R. So when you work those numbers out, you have 6 is equal to 4.1664 plus 1.92 R. That's the way that all works out there. So to work out R, then 1.8336, you've taken this over here and taken it away, is equal to 1.92 times R, and R comes out to be 0.955 ohms or 0.96 ohms. Part C. Figure 5.1 shows a battery of EMF E and internal resistance R. The battery is connected to a variable resistor. the resistance of the variable resistor is gradually increased from 0. On the axis of figure 5.2, sketch a graph to show how the current in the circuit depends on the resistance R of the variable resistor. Now, obviously current is proportional to 1 over R, but we also have the fact that there's a fixed resistor in there, so there's always going to be a resistance. So there has to be a finite value here of I. It can't go on forever, so we have to start somewhere, and we're going to go down, as it's an inverse proportion relationship. On the axis of figure 5.3, which is the graph beneath, sketch a graph to show how the power developed in the variable resistor depends on its resistance R. The value of R on the horizontal axis is that of the internal resistance of the cell. And so you can see there's the internal resistance of the cell, and you know already that you get maximum power transfer whenever the R is equal to small r. And so it's a graph which goes up from 0 to a peak and then kind of levels off a wee bit like that. Well, drops, I suppose. And you get 2 marks for a curve from 0, because obviously when you've got no resistance, you've no power transfer, and it has a maximum value at the place where R is equal to small r.